Welcome, everyone. Today we are going to dive into one of the most significant architectural shifts happening in the world of artificial intelligence, the Model Context Protocol, or MCP. If you have been following the rapid rise of AI agents, you've probably realized that we are transitioning away from simple chat windows and moving toward autonomous systems that can actually get work done. But behind the scenes, developers have been hitting a massive wall. MCP is the open standard designed to solve this. Think of it as the universal USB-C port for AI. Just as USB-C standardized how we connect power, screens, and data storage to our laptops with a single physical connector, MCP standardizes how any large language model safely connects to any database, enterprise tool, or local environment. Let's explore why this protocol is becoming the default infrastructure for the agentic era. To understand why we need a universal standard, we have to look at the fundamental nature of large language models. At their core, natively, LLMs are just highly advanced next-word predictors. They excel at pattern completion and language reasoning, but they possess absolutely no inherent agency. They are essentially trapped inside a digital text box. Without external help, a model cannot query a database, read your local code files, check the weather, or send an email. It knows how to think in language, but it has no hands to interact with the physical or digital world. To make an AI truly useful in an enterprise environment, we have to build bridges out of this text box. But until recently, building those bridges was an engineering nightmare. Before MCP, the typical way to connect an LLM to an external tool was to write bespoke custom integration code. If you wanted your agent to look up customer data, you wrote custom code for your database API. If you wanted it to coordinate schedules, you wrote custom code for your calendar API. This created what we call adapter bloat. Developers spent more time writing and maintaining glue code than actually building intelligent systems. Worse, this setup suffers from instant breakage. The moment an external service updates its API or changes a single parameter, your custom integration code breaks instantly, and your AI agent goes offline. When you attempt to stack multiple custom tools together to build a complex, multifunctional assistant, it quickly becomes an unstable, completely unscalable engineering bottleneck. This is the exact problem the Model Context Protocol solves. It replaces custom API spaghetti and brittle connections with a universal translator layer for the entire AI ecosystem. Open-sourced by Anthropic, MCP is rapidly becoming the industry standard. Instead of writing custom adapters for every single combination of AI model and data source, developers now build to a single protocol. MCP sits directly between the LLM and your external tools, translating dozens of different APIs into a single unified language. Once a service builds an MCP server to expose its data, any compatible AI client can plug into it instantly with zero custom coding. It is true plug-and-play integration for artificial intelligence. Let's look under the hood at how this actually works. The brilliance of MCP lies in how it decouples the AI interface from the underlying data source. The architecture is split into three clean layers. First, we have the MCP host. This is the parent application that the user actively interacts with. It includes chat applications like Claude Desktop or developer environments like Cursor and Windsurf. Second, inside the host, we have the MCP client. The client is a library embedded directly inside the host application. It is responsible for initiating sessions, handling protocol translation, and routing requests outward. Third, we have the MCP server. This is a lightweight, dedicated, and completely decoupled process that communicates directly with external resources, like your databases, files, or local secure containers. Because of this separation, the parent AI application never needs to know how the underlying database works. It only needs to speak the standard MCP protocol to the server. To keep these interactions safe and structured, MCP divides all AI capabilities into two primary categories: resources and tools. Resources represent the GET context. These are strictly read-only data sources that the LLM safely consumes to gain context. Think of things like local text files, read-only database queries, Kafka streams, or static CSV attachments. The AI can look at this data to inform its reasoning, but it cannot change it, ensuring there are no accidental side effects. Tools, on the other hand, represent post actions. These are actionable, dynamic capabilities that enable the LLM to execute code or perform mutations with real-world consequences. Examples include writing to an SQL database, executing local terminal commands, making payment calls, or modifying a code file. By cleanly separating read-only context from actionable tools, enterprises can maintain incredibly tight control over what an AI is allowed to do. Of course, when you give an LLM access to actionable tools, you run into a major risk. Hallucinations. LLMs are notoriously unstructured, and if a model tries to invoke a database tool with the wrong parameters, it can cause severe errors or system crashes. MCP solves this by enforcing predictable execution through strict schema validation, typically utilizing ZOD schemas. When a server advertises a tool, it defines the exact input parameters and data types it expects. The LLM's unstructured output must pass through this rigid validation layer. If the model attempts to generate a malformed request, the schema validation blocks it, forcing the LLM to format its intent precisely. This active guardrail virtually eliminates model hallucinations during tool execution, making agentic workflows safe for production environments. Another key benefit of MCP is its ability to scale seamlessly from a single developer's laptop to secure enterprise-grade cloud networks. It does this by supporting two distinct types of transport layers. For local transport, MCP uses standard input and output, commonly known as STDIO pipes. This allows the AI client and server to communicate as local subprocesses on the same machine. This approach features virtually zero latency, requires zero network overhead, and is incredibly secure, making it ideal for local container environments like Docker Desktop. For remote transport, MCP transitions to HTTP and server-sent events, or SSE. This standard enables secure, streaming, asynchronous notifications over standard web protocols. It is designed to bridge local AI clients to remote, highly distributed cloud infrastructure and centralized enterprise databases securely. As organizations begin deploying dozens of different AI agents and tools, managing individual connections on every developer's machine quickly becomes unmanageable. This is where gateways enter the picture. A centralized gateway, such as a Docker MCP gateway, acts as a single orchestrator for fleet-wide AI integrations. Instead of configuring dozens of individual server connections inside a local config file, the AI host connects to one centralized gateway. The gateway then orchestrates, mounts, and safely manages secrets for dozens of containerized MCP servers simultaneously. This architecture allows IT and platform engineering teams to maintain centralized visibility, enforce global security policies, and manage access controls across the entire organization. Looking forward, the standardization of MCP opens the door to incredibly sophisticated multi-agent ecosystems. A prime example of this is the emerging agent-to-agent, or A2A, protocol developed by Google. While MCP standardizes how a single agent connects to tools, the open A2A standard standardizes how independent AI agents collaborate with one another. Under this model, specialized agents can autonomously query one another to discover capabilities and dynamically delegate subtasks. For example, a flight agent can package up travel dates and dynamically delegate the accommodation booking to a specialized hotel agent. The agents negotiate inputs, manage the task lifecycle, and synchronize results as a cohesive, intelligent network, rather than operating as isolated, siloed bots. We are witnessing a fundamental paradigm shift in software development. The industry is rapidly abandoning the old model of building bespoke, tightly coupled bots from scratch. Instead, we are entering the App Store era for AI. With the rise of centralized registries like Pulsar.com and community hubs like Awesome-MCP, deploying new capabilities to your AI is becoming a simple, one-click experience. Whether you need to connect your agent to GitHub, a PostgreSQL database, Slack, or Stripe, you can now spin up containerized, pre-built servers instantly. By standardizing the connection layer, the Model Context Protocol has unlocked the true potential of agentic AI, moving us closer to a future where intelligent, secure, and highly capable AI assistants work seamlessly alongside us.